especially dyes, can be used for nonlinear electro-optics. So he actually sort of did his bachelor's of science in chemistry from MIT. In the year I was born, he got his BSc degree in 1978, and then he moved on to University of Wisconsin at Madison, where he did his PhD degree, post which he was a postdoctoral researcher at Oxford, actually Professor Malcolm Green's lab. His deep-rooted interest in organometallic chemistry and chemistry in general has been well known for a long time, and it's actually a gift that he used chemistry, gift to all of us, that he used chemistry and showed the way to many of us of how to collaborate and learn new ideas, and especially move into photonics and nonlinear optics with the ideas of making materials, new materials, and looking at nonlinear phenomena. Of course, based on this fundamental work and showing the way to many chemists, especially in applications, he has been in very important and significant positions. Especially, I would like to mention that he is actually the chair of the editorial board of Materials Horizons, one of the most important journals in the materials community. His work has been recognized by multiple organizations, some of which I just wanted to say that he is a fellow of the Optical Society of America, OSA. He is actually a fellow of the Royal Society of Chemistry, as well as the American Association of Advancement of Science, as well as, of course, the American Physical Society. Without further ado, I would like to welcome again Seth, and all from the side of TIFR. We are glad that you are giving us these tutorial talks, which actually are enabling us to understand a lot about organic dopants. Okay, so thank you, Seth, and please you can start your lecture.
Thank you so much for the kind introduction. So yeah, today I'm going to be talking a bit about the applications of these so-called redox dopants for organic electronics and optoelectronics. But as the issue of Lewis acid doping came up yesterday, I just thought I'd take a couple of minutes to talk a little bit about that, and the fact that I think that people have been using them, I guess, for the last 5 or 6 years, and I became aware of that. And I saw what people were saying about how they worked. And as an organic chemist, a lot of what I heard people talking about simply made no sense to me whatsoever. And so I began thinking about that. And really, I can tell you, I was doing a sabbatical about 3 years ago. After having thought about that and seeing some talks by Dieter Nayer's group in particular, and talking with Norbert Koch, I decided that not only did I have to say what I think is going on is wrong, but I had to make some sort of attempt to educate at least my colleagues about why it was wrong and what could be going on. So, yesterday we talked about simple versus complex dopings, and we talked about one electron things as dopants. And yesterday we talked about non-innocent dopants. We focused on the DMBIH, but there are other cases where people have used, I would say, non-innocent end dopants. I didn't talk about fluoride doping. But we did mention the photo-induced electron transfer from triarylamines, which is shown on the right here. Today, I'll just talk a little bit about, I'm not going to talk about the lithium TFSI, that's its own story, but these Lewis acid dopants that are often based on arylated boranes, and in particular perfluoroarylated boranes are related compounds. So there was an observation that was made, and this was a paper, as I said, by Dieter Nayer, that when you treat P3HT with perfluoro triphenylborane that you can generate polarions in very high yield. But the reality of this, and this is work that's in the literature, is that the anion of perfluoroaryl borane, it's not stable, okay? So there are a couple of things that are worth noting here. So first of all, what I show you is the reduction potential versus ferrocene. And what I'm telling you here is that it's not easy to reduce, right? It's pretty hard to reduce. So it's not a strong oxidant, okay? The electrochemistry itself is only reversible at very, very high scan rates, okay? And in this particular paper that I referenced, number 2, people have looked at this and they found out that when they put these things into electrochemical systems and they did electrochemistry and they isolated what you see after the reduction, okay, in dichloromethane. There's a ton of different things in there, okay? None of which is a triarylborane radical anion. So even if you made it, which you won't from P3HT because it's not a strong enough reducing agent, okay? The fact of the matter is that it decomposes. So this goes to the issue that you have no idea what your anion is. So then the question is, well, how does it work? And then some people suggested, well, you know, it basically dopes by coordinating to the sulfur, and that was sort of, you know, what happens. You know, the spectra are really not consistent with that, okay? So once again, I point out that it helps to know the literature. And in this particular case, the literature is done by my former postdoc advisor at Oxford named Malcolm L.H. Green, who passed away last year. And he was an absolutely brilliant and one of the most creative chemists I've ever met. So he published a paper on the fact that when you work with these sandwich compounds that I referred to yesterday, and not even these very easily oxidized cases, but just regular sandwich compounds, that if you react them with this perfluoroborane, you do in fact get oxidation products. And unlike the people working in organic electronics, okay, who mix stuff up and measure a conductivity, as an organometallic chemist, what he went and did was to isolate the products and actually structurally characterize them using X-ray crystallography, okay? And the reality is that the reaction is nothing as simple as what you think. And the reality is that the reaction does require water, and that because the perfluorotriarylborane is very Lewis acidic, if you're not scrupulously careful, there will be water. And the triarylborane will create a water adduct, which is shown here, okay? And that's itself a pretty strong acid. Okay, now, if you look at the reduction potential of H+, okay, it's minus 0.7 volts in water versus ferrocene, okay, not 1.8 volts negative of ferrocene, okay? And if you consider that in a poorly solvated, non-aqueous solvent, okay, it's going to be stronger. So the reality is that what happens is that this reacts, and from a stoichiometric perspective, you lose half equivalent of hydrogen. This is not to say that this is mechanistically what happens. You end up with this material perhaps transiently, and then what ultimately happens is that that reacts either with an other equivalent of the water adduct or an other equivalent of the triaryl borane. Now, how do we know that? And the answer is because he literally isolated, characterized, and has crystal structures of these compounds. Now, which one of these anions is present in these polymers? I don't know yet. Quinn Yen just sent me this morning a revised version of a white paper for a proposal to the Department of Energy, where, among other things, trying to sort this out is part of it. But what I can absolutely tell you with a very high degree of certainty is that it's not this, which is the anion, and it's certainly not a radical anion of that. Okay? So when this work was done, and I sat down with Quinn and explained this to her damn near 2 years ago in a meeting in Spain. Okay, and I actually put the slides that you saw up in the meeting in Spain. Okay, and she basically contacted a good friend of ours, David Beljean, who's in Mons, Belgium. He was from the Jean-Luc Breda group of graduate students, who's now a very well-known theorist on himself. And he did a bunch of DFT studies. And he basically showed that the mechanisms that would involve any loss of hydrogen to give something like this were both kinetically and thermodynamically unfavorable. But when we showed them, okay, again, the fact that this is not what's made, and certainly, as I said, the radical anion of this is not what was made, they recalculated the system, taking into account formation of these products. And lo and behold, okay, the delta Gs for these reactions went from being positive and thermodynamically unfavorable to negative and thermodynamically favorable, okay? And so the point is that, and what's not shown here is the loss of hydrogen, okay? So the point is that what's happening here is you are having coupled reactions, and critically, the formation of these delocalized or mixed valence, I'm not sure which, ions is essential to driving the thermodynamics in a direction to make this reaction favorable. Okay, so I hope for the young man who asked me questions about the thermodynamics that these slides will be helpful in explaining, in fact, why, you know, separately from the Le Chatelier's principle with loss of hydrogen, why thermodynamics still seems to hold for reactions, okay, when you take into account actually having the correct products of the reaction. Okay, so with that, my slides are stuck again. I'm going to turn back to where I was going earlier and say that now we're going to talk about some applications of these dope. By the way, this paper, that the theoretical paper that I just mentioned is currently under review. And I actually, given that David is the lead author and my colleague Steve Barlow and I, our role was to try to bring the chemistry to the theory. I'm not sure what the status of the paper is right now. Okay, so I'm going to talk a little bit about applications of N-dopants.
There is a question. Showman Kundu, do you have a question? Showman, do you have a question?
Oh, I think he's talking with someone else there.
Okay, no worries.
Yeah,
oh, sorry about it.
No worries, no worries. So I'm going to talk a bit about these dimeric dopants and actually some of the hydride dopants and their applications. And you can see that we're going to talk about solution processable and vacuum processable things just for doping, some fundamental studies of trap filling, okay, a bit of contact doping, modification of work function of standard inorganic electrode materials, modification of work function of 2D materials like graphene and metal dichalcogenides, a bit about electron injection into OLEDs, and actually doing things that is thermodynamically uphill. And I'll explain that. And then maybe a little bit on a couple of other things if I have time. Okay, so let's talk about trap filling. So as I said yesterday, trap states are important in terms of trying to get high mobility. So if you have traps, your electron is going to move slowly. But if you can fill those trap states, then you would think that the energetic barrier for the electron moving, okay, will be higher. Okay, and so what I'll mention is that using photoelectron spectroscopy and or inverse photo emission spectroscopy, if you can really map out a bit the density of states, and this is a work that Antoine Kahn is truly expert at. And so this is a study that we did with Antoine. I think more precisely, this is a study that Antoine did with us. And the idea was the following, that we would take a material that might have had some traps, okay, and not terrible number of traps, but there are traps, and that we would add a dopant, okay, where the HOMO was in fact above the transport level, okay, of the material, okay. And initially what we would do is we'd add enough of this to fill the trap states. But if we actually had a dopant density above the trap density, then what would start happening is that we would fill the what we would call the transport states. And now what we would see is not only a modification of the mobility, but we would really start seeing a relatively large change in the conductivity. Now, if you imagine that these trap states are distributed over a broad energy landscape here, but there were very few of them, okay, then as you added a bit of dopant and you rapidly filled them, what you would begin to see is the rapid change in the Fermi energy level, okay, as it moves up towards the transport level, the LUMO, okay? However, once you get into the regime of filling these levels, which are there at a bulk density as opposed to a very low trap density, then it's going to take quite a bit more dopant to appreciably change the Fermi level. Okay, so the example that we used is to take C60 and a ruthenium dimer that we had made and to dope that. And that was done under ultra high vacuum. And Antoine had the system equipped with a quartz balance system where he was able to control the molar ratio from 10 to the minus 4 to 10 to the minus 1. So from 10 to the minus 3 mole percent to 10%. Okay, and as I said, he examined the energy level using UPS and IPS, and then there were transport measurements done. So if you look at this, what they saw is at very low dopant concentration, initially, a very rapid change in the HOMO peak position, which obviously, maybe not obviously, corresponds to a decrease in the work function until they hit somewhere between 10 to the minus 3 and 10 to the minus 2 mole percent. And then it really had a different slope. And the notion was that at these low concentrations, what was happening is that you were basically filling these trap states and pushing up the Fermi level up against the LUMO. But then around this concentration here, I hope you can see my cursor. Okay, around this concentration here, boom, you started hitting the transport levels. And now it's going to require an awful lot of dopant to significantly change, okay, the Fermi level or the work function. Okay. And this was actually modeled by Jean-Luc Breda. And an interesting thing, as I mentioned, okay, is that first of all, you do see an increase in the conductivity when you, or in the mobility, okay, when you dope C60. So let me show you, ignore all the stuff on the left of this slide. That's basically just the hard data from which the bottom line is extracted. And colleagues like Bernard Kippelin, okay, thinks it's absolutely critical for people to see that you have very good data. And there's good data. Let's focus on the right side of the slide. So what we did in this experiment is we took as received pure C60. This is kind of a high quality C60 that we got from Aldrich. Then what we did was we took that material and we sublimed it, I think, 3 or 4 times. And then it was very, very pure. Okay. Then what they did was they made transistors out of these materials. Now, when you took the pure C60, you ended up with a turn-on voltage of 18 volts. That's the threshold voltage, okay, between the gate and the drain, okay? And then if you doped it, what you can see is that, again, at 10 to the minus 3 mole percent, okay, that threshold voltage dropped to about 4 to 5, okay, volts. Okay. And that was done retaining a good on-off ratio for the transistor. In other words, we were not putting an appreciable number of electrons into the LUMO of the C60, generating free carriers. If you went beyond that, okay, then you'd start seeing a substantial increase in the conductivity, and you'd basically see things that is approaching an ohmic type of system rather than a diode, okay? Then what we did is we examined that relative to the highly purified C60. And you'll notice that the highly purified C60, okay, ends up with a turn-on voltage that's equivalent to the C60 that was as received with 10 to the minus 3 mole percent, okay? And so the point is that what we've done here is taken something that was not that pure, and by adding an impurity, as someone said before, a dopant, but at a very controlled level, we changed its performance in a transistor to match pretty much that of a highly purified material. So here, what the dopant is doing is taking something that I would say most people would, you know, if you went and did elemental analysis on the as received C60, it would look really good, okay? But as anyone who's worked in the area of organic electronics know, in many cases, the electronic properties are truly the indicator, and a much more sensitive indicator of material purity than things like elemental analysis or mass spec, because, you know, carriers at the level of 10 to the minus 3% are a hell of a lot of carriers to change the electronic property. But if you measure elemental analysis, okay, your uncertainties are much greater. NMR, you can see percent, maybe tenths of percent, but very small levels of impurity are hard to detect. Okay, now
can I ask a quick question, because I'm kind of unfamiliar with the plots you were showing?
Yes.
Can you explain the bottom right VTH volt versus doping ratio? Can you explain what the plot means?
Yes. Okay. I'm sorry. So what they've done is, this is a series of different doping experiments where they go from no dopant to 0.5 molar ratio of dopant,
okay,
up to 3 times 10 to the minus 3, mole percent dopant.
okay.
Okay. And the VTH is the threshold voltage that's required to turn on a transistor.
Okay. Good.
Now, if you have a lot of traps,
Right.
okay, then what you have to do is to drive up the voltage to a sufficient high level to fill the trap states before you get a current flowing between the source and the drain.
Right.
Okay. Thank you, because if you didn't see that, many other people didn't as well. Okay, so here's the point, right? At the very beginning of this talk, at the very beginning of yesterday's talk, I said, you want to know what's in your system and you don't want impurities. So a very logical question would be, okay, you can take this C60 and add some impurity to it, the dopant, and make it look like the purified C60. But why would you do that? If you want to make a high quality device, why wouldn't you just go and sublime the material 5 times and get it really pure, not have this other stuff around, and go with that? And the answer is you would, if you're working with a material that can be purified by sublimation. But this goes back to the comment that I made earlier, that certainly some of the small molecules that people make, quote small molecules that people make, can't be purified. I'll just give you an example, and I'm not saying that you necessarily would want to make a transistor out of this, but if you look at some of the non-fullerene acceptors that people make, they're sufficiently large and sensitive that they would decompose upon sublimation. Okay, so there's the issue of molecules that would decompose upon sublimation that would not be able to be purified that way. And then there's the issue of polymers, where you just don't have that option. So the dopant here may actually act at some level as a thing that you can have, and I'm going to use this phrase a few times, in your toolkit. Okay, think about us as a woodworker making things, and we have a variety of different tools that we can make things. Okay, the tools might involve synthesis, they might involve different processing techniques, so that at the end of the day, we envisage whatever it is we want to make, a cabinet, a chair, and we use all the tools that we have to make a quality piece of furniture for the sake of argument. Okay, so what I'm showing you is that here is a case where one of the tools in your toolkit could be a dopant. Now, a recurring theme that I want to make clear to people is that you have a toolkit that has many tools, okay? And a dopant is one. It's not the magical tool that does everything. If you need to saw a piece of wood in half and your dopant is a screwdriver, okay, you're better off using a saw, okay? But if you have a screw that you need to get screwed into the wood and all you have is a saw, it would be nice to have that screwdriver in your toolkit as well, okay? And it may turn out that you need a Phillips head and that this is, a non-Phillips head screwdriver, or there are different sizes. And so the dopants, okay? It's not that you just have one, I'll use an example, Allen wrench in your toolkit. You may need a set of Allen wrenches to match the particular application, okay? So I'll just point out that you can also impact the injection barrier for putting charges into things. And I'll point out that if you have an electrode, for example, where the work function is substantially higher than, in this case, the HOMO level, as I show on the left, if you do a bit of p-doping, okay, of the system, what you can do in a manner that's analogous to what I showed where we were doing n-doping and moved the Fermi level towards the LUMO, if you do p-doping, you can move the Fermi level towards the HOMO, okay? And in that case, what you can end up doing is shifting them. And in some cases, you can get, if you allow those two things to interact, i.e. the electrode and the molecule, okay, you can get some partial charge transfer from the electrode to the material, okay, or vice versa, okay? And that can lead to band bending and what's called the depletion region. I'm not going to get into that into great detail, okay? And this is relevant because, you know, in some cases, you end up, for example, making a transistor, and a lot of people report mobilities of a material by making a transistor. And what one needs to really understand is that you're not reporting the mobility of a material. You're reporting the current density in a device, okay, that has a material, but it also has other factors that can affect the current density. For example, things called the contact resistance, the resistance between the contacts and the material, okay? And so if that resistance is high, you could have a wonderful material, but your current density is going to be low, okay? And it's only in the case where the limiting factor, okay, is the mobility in the material that the measurements that you get from doing a analysis of data from a transistor is really somewhat reflective, quite reflective of the material properties. So in this particular,
sorry, sir, there's a question. Yeah, first by Professor Nagafani and then by Professor Ravi Kishore. Okay, Naga, Fani?
Okay, yeah, so a quick question. I mean, when you showed those, the drop in the threshold voltages when you purified C60, now, how did you definitely say it's only trap filling and it's not the contact potential changing at all or the injection barriers changing at all? So I would think as you purify the material, you might, I don't know, maybe not have any more Fermi level pinning with the contact, with the injection contact. And maybe for that reason, your threshold voltage could change when you change the purity. Is there a reason why we could totally eliminate that as a possibility?
well, I think that I may not be understanding you correctly, but I think that when you say that you're changing the Fermi level pinning, at some level, those are one and the same thing, okay? The trap filling is moving the Fermi level up, okay? And so you are in fact changing the Fermi level. So you're doing, you know, that is what the trap filling is doing, okay? It's basically pushing the Fermi level up, okay, towards the transport levels. So
would you say the injection barriers have changed as well in that plot that you showed?
Likely, okay, and that's what I'm going to show on this slide specifically. So I want to point. Let me just go through this slide, and then we can revisit your question if it's less clear, if it's still unclear. So in the previous slide, the C60 across the entire length of the the transistor was doped. Okay. In this case, what was done is that in the channel, the material was not doped, but using shadow masks, okay, 3 nanometers of the dopant was put right where the source and drain electrodes were deposited and would be deposited, and then those were deposited on top. So going to your question here, what we did is we changed the injection barrier, but without changing the bulk material within the channel. So in one case, we changed everything, and that may have varied the contact resistance, okay? But in this case, what we tried to do is only vary the contact resistance, but without changing the material within the channel, okay? And so here, what we see, and by the way, I think another point that's worth noting, right, is that when we do that, the first example, we try to not substantially change the conductivity of the system. Here, underneath these things, by virtue of the dopant being in contact with the C60, okay, right in this region, it is pretty heavily doped. So only under the contacts, it's heavily doped, but in this region in the channel, it's not. Okay. And so then what you see is that the effective mobility goes from 0.5 centimeters squared per volt second up to about 1.6, 1.7. So it about triples, okay, which is concomitant with the contact resistance, which they extract by doing, you know, these transmission line measurements, okay, goes down by a similar amount. It goes down, it goes from, you know, 40 down to about 15. So there's about a factor of 2.5, 3 decrease in the contact resistance, and there's about a factor of 3 increase in the measured conductivity, okay? And so, and by the way, all these materials retain good on-off ratios, which is consistent with the fact that we're not having the dopant kind of migrate into the channel. So I think that, you know, what you suggested is that, yeah, there could have been an impact of doping on that contact resistance, okay? Here, we ensured that there was, okay, a good level of doping because we put enough material to pretty heavily dope and change the conductivity of the material between the electrode and the intrinsic C60. Does that clarify?
Funny?
Yeah, terrific, actually. Just one quick question as a follow-up. How much did the threshold voltage change by between the two devices, the device where you did not dope near the contact and where you did?
You mean not in the experiment shown here, right?
Yeah, in the one that's shown right here.
Honestly, I don't remember.
Okay. Do you think it's as substantial as what you saw like 2 slides prior to this?
I'm sure. I'm sure it would be.
Okay.
Well, actually, I shouldn't say that because let me take that back. I'm not sure it would be because you still have in this system trap states in the channel. Okay, so the fact that we make it easier to get charges into the material doesn't mean that, well, it's not consistent with us actually filling the trap states. Okay, and the fact that the conductivity stays extremely low means that the threshold voltage might not have changed. And what I'll have to do is ask you, and these slides are going to be available to everyone. I think you'd have to go back to this applied physics letters paper back in 2013 and take a look at that. And just to be super honest with you, as the chemist in this interaction, I probably didn't pay close enough attention to that in the first place. And as someone who in 4 months plus a few days will be 60, okay, my memory from what we did 8 years ago, even if I did pay attention, is probably not good enough to tell you.
Okay. I'll give back to the paper, yeah.
Okay, so here's another example. I ran into Mark Hersam at a conference, and he was talking about some beautiful, beautiful work that he was doing on making transistors out of carbon nanotube arrays. But they were p-channel transistors. And I asked him, I said, Mark, do you think that we could basically very, very, very lightly dope these materials, okay, in a manner to like what we did with the C60, to shift the Fermi level, okay, up towards the conduction band of these things and have them behave as N-channel transistors? And so he said, let's give it a shot. Now, there's too much data here, and I should have asked him to send me plots. This is actually literally cutting out data from the paper, okay? But the bottom line is they did these with different levels of doping, and I just want you to focus on the purple, okay? So they did some doping for on the order of...
Sorry, blocking you again from explaining. Could you just give us a sense of the device architecture? Why this architecture for this measurement? The way you have placed nickel, then the aluminum oxide, and the silicon dioxide.
That I can answer definitively. No.
Okay.
I cannot. Okay, and you know, this is a device architecture that Mark had spent quite some time optimizing. He didn't explain it to me. It was well known at the time. The only thing that I can tell you is that he had this optimized device architecture for what he was doing with N-channel transistors. And we said, you know, what if you basically expose the carbon nanotubes to a dilute solution for 10 seconds, okay, just 10 seconds, okay, before you deposit the alumina and the nickel. That's what I can tell you. The rest of it, I just can't, I don't know, okay. And so what happened is they end up making N-channel transistors. They end up getting something with a, you know, a pretty good on-off ratio. These are basically histograms of the frequency of the number of devices. And you can see here they made 1,200 devices, okay? And they end up, you know, getting this histogram of the performance. And they end up showing that they get a relatively low threshold voltage. And this work, okay, they end up getting mobilities. Now, these are N-channel mobilities on the order of maybe 2 or 3 centimeters squared per volt second. So what we've done in this experiment is taken a p-channel material, okay? We didn't go and invent a new material. We just exposed it to a very dilute solution of the dopant for 10 seconds. And now, boom, you have an N-channel material. Okay. I'll point out that we've done some work with other people where now they're seeing things that have mobilities on the order of, I think, 8 centimeters squared per volt second. And it doesn't change that much in air. Okay. I didn't include that data here. Okay. Now I'm going to talk about modification of the work function of materials. So these dimers, okay, and it's not unique to these dimers, other things will do it, okay, can basically dump electrons into the conduction band of a electrode surface. Now, when they do that, okay, what has to happen is that the electrons go into the conduction band. Okay, it's a you know, these are good semiconductors. It's ITO. So the electrons will delocalize into the conduction band. Okay, but the negative charges within the material need to be compensated by positive charges on the surface, which are the positive charges left on the ions of the dopant. So when you do that, you create what's called an interface dipole, and that interface dipole leads to a shift in the vacuum level. And as you know, the work function is defined by the difference in energy between the Fermi level and the vacuum level. And so if you shift the vacuum level down by creating this interface dipole, then what you would expect to see is a reduction in the work function. And what I'll point out is that for electron transport materials, you want materials that have a relatively low work function in order to inject charges. Okay, so here is a slide. This is a slide that is done with work with Norbert Koch. We published a paper a few years earlier where we did things only by solution doping. This is a case where they did both solution and vacuum deposition. And of course, the vacuum deposition allows them to, you know, just have a cleaner system. Okay. I can't remember. I think our paper might have, I don't remember where our paper was published, but it was published a couple of 3 years before this paper with Norbert. So what they do is they have a substrate that has a certain work function, okay? And that's shown by the black line. So you can see here a variety of different materials, okay? ITO, gold, silver, P dot, clean gold, moly trioxide. So those are the work functions in the absence of doping. Then in red, they evaporate 1 to 2 nanometers of the dopant on that surface. In blue, they drop cast in toluene, okay? And then they do 2 experiments. 1, they measure the work function. 2, they let it sit in air for 5 minutes, okay? And then on the solution ones, they do a couple of things where they let it sit in air for 5 minutes, okay, and then 24 hours, okay? So the point is that if you look at every one of these materials, okay, there's a substantial drop, like 1.5 volts drop, okay, in the work function, okay? And in fact, for just about all of these, with the exception of doping the moly oxide, the work function goes below 3 electron volts, okay? The second point is, which is pretty low, okay? And I'll show you on a couple of slides, it's really quite low. The second thing is that when you actually put this in air, okay, for a bunch of these, with the exception of the P dot, which can probably de-dope, okay, it stays relatively low. And that your solution doping is not quite as good as the vacuum doping, but it's not bad. So here's an interesting experiment that was done by Norbert and his colleagues, and I'm not going to go into all of the motivation for why they chose to do this, but what they wanted to do was make a hybrid LED device where they were going to generate the excitons in the device into zinc oxide, and then ultimately deposit a highly emissive molecule on top of that. So they would try to generate the excitons in the zinc oxide and then have energy transfer to a material sitting on top of that. So the first thing that I want to point out is that they, in this process, and you'll see why on the next slide, they examined the impact of N-doping of single crystal zinc oxide grown in ultra high vacuum. Okay, and so what happened is they could actually determine by virtue of how they grew this, whether it was zinc terminated zinc oxide or oxygen terminated zinc oxide. And the work function of zinc terminated zinc oxide in UHV is 3.7. Okay. And the work function dropped to 2.2 electron volts. Now, for reference, calcium has a work function of 2.8. So by depositing on the level, in this case, of 5 angstroms, about a half a nanometer of this ruthenium dopant onto the zinc oxide, they ended up making a material that had a work function that was 0.6 electron volts lower than that of calcium. Okay, and again, this is mostly an interface dipole effect. Now, here is the system that I alluded to earlier. And here was the concept. The concept was that they were trying to have an exciton in this layer of zinc oxide, okay, which was maybe not so emissive, okay, but it was very easy to generate the excitons in it because of the electrical properties. And then what they wanted to do is do energy transfer to this molecule developed by Stefan Hecht at their institute, which for whatever reason they call LP4SP3, okay? I suspect that the LP4 has to do with the 4 phenyl groups and the SP3 has to do with these groups here, okay? But whatever the case, they designed this molecule to have a gap that was just a little bit lower, tiny bit lower than this, so that than this material, so that you would get energy transfer. And so that was all good, except that there was just a little bit of a problem of the alignment of the LUMO with the conduction band. And the problem was the HOMO was right where they wanted it to be, okay? But the LUMO was a little bit high relative to the bottom of the conduction band, such that when they ended up doing energy transfer to this LP4SP3, they would get a back electron transfer to the conduction band to form, I guess, what you might call a charge transfer exciton, where the hole was here and the electron was there, and that was not emissive. So then what they did is they deposited something on the level of a nanometer, okay, of this dopant. And that led to a bit of doping of the conduction band. And it just slightly pushed up the level of the conduction band relative to the LUMO. It basically pushed up everything a tiny little bit relative to the LUMO of this molecule. So now the HOMO is actually very well aligned, but it brought the LUMO to a point where it was slightly lower. So what are the consequences of this? Okay, well, in this slide, okay, what you see is in blue, the emission characteristics in the undoped material. And in green, just a tiny bit of dopant, as I said, on the order, you can see it says monolayers. Okay, so, monolayers of dopant. Okay, boom, the emission turns on. So here again, in the toolbox, they made these two materials. They kind of had almost everything that they needed. And I would say in this case, the dopant kind of worked a little bit like sandpaper. It allowed you to kind of just slightly, tune the property to give you the band alignment that you needed. Okay. As well as leading to a relatively low injection barrier to inject electrons if you wanted to. That's a separate thing. Okay. The same kind of thing can be done on two-dimensional materials. Okay. So here, this was done by depositing, okay, a rhodium dopant on graphene. Okay. And we first published this in 2014, doing it in solution. A couple of years ago, Antoine went back and did this by vacuum deposition. And again, saw a more profound effect. But the difference here is that this is a single layer system. In the case of the electrodes that I referred to before, the change in the work function is basically solely defined by a shift in the vacuum level. In these systems, okay, the change in the work function is not only defined by that, because you only have a monolayer of the material. If you start doping, you start actually filling the Dirac cone that is unoccupied. So you're actually doing two things. One is you're filling the empty conduction band. It's now being not empty, and you're shifting the vacuum level. And you can do the complementary thing with p-dopants. Okay, you can p-dope these and deplete the valence band. Okay, and by doing this, in this particular case, we varied the work function by 1.8 volts. Okay, and in another case with Antoine, we can extend that to over 2 volts. So by and large, we can take graphene, one material, p-dope it, and make it sort of much, it might mean much more, but better as a whole injection material. Or we can n-dope it, okay, and make it into a very good electron injection material. And I don't believe I have the slide on Antoine's work, which, by the way, Satish, at that FPI meeting that you were at in Berlin, he reported upon. But in that work, he's shown that just by taking a monolayer of graphene and doping it with one of our n-dopants, you can make it into a very, very nice electron injecting material.
Okay. Yeah.
Okay.
So, Seth, I have a question. See, last couple of slides, you have been talking about changing the work function of the electrode by introducing these dopants.
Mm-hmm.
And we have this thin layer of a dopant. On top of that, when you deposit the active layer, there will be a diffusion. And, in addition to changing the work function, is this dopant, do they also dope the active layer?
The answer is not really. And I tell you, so there are two issues. Okay, if they do, they do so. Well, this is it. Let's just go into this, okay, a little bit. But the answer is that ultimately they're going to do it once everything's in contact. Okay, if you think about it, the dopant can either dope the active layer or not thermodynamically, and it can dope the electrode. So let's assume you just say, okay, I'm going to dope the electrode. Okay, well, then the electrode has a monolayer of ions, and then it has the active layer. Where are the electrons going to end up at that interface? And the answer is wherever they want to be, right? Because they're allowed to be, they're in electrical contact. So there'll be maybe some electrons in the active layer and some electrons in the electrode, okay? And then the other question is, well, what about just the diffusion of the cations? And the answer is that basically Antoine has made systems and has kept them for a long time, and the properties don't change much. So that suggests that at least to a first approximation, after the electrons are equilibrated, being wherever they want to be, the system seems to settle down. Okay. Now, what I can tell you is we've done this kind of doping by solution and by vacuum deposition. And one of the concerns I've had is, well, when you solution process, you could actually de-dope and wash things off. And in some cases, we've seen that. In some cases, we haven't. But I'll just tell you what what our approach is in terms of thinking about that. Okay. Have you seen there's well, I don't even need to get into that. Let me just not go by analogy. Let me just give the simple picture. Okay, let's assume we want to take an oxide and we want to dope it. Okay. And we're worried about the ions going away. Let's assume it's ITO. Okay. Well, our group has done a ton of work over many years of modifying ITO with phosphonic acids. Okay. Yeah. So let's assume we modify the ITO with a phosphonic acid that is cationic, has a pyrididium. And so we deposit the phosphonic acid, there's a counter ion. Okay, I call it chloride. I don't really care what. Then we take that material and we dip it into any reducing agent, call it our dopant, and we dope the ITO. So then we make a cation from our dopant. We have the chloride. We wash all that away. And then what we've done is we have pinned the cation to the surface so that it can never go away. We've made it electronically something that is essentially inactive, and then we fixed it there. And in a very similar way, you could imagine doing that by essentially depositing a very thin layer of a charged polymer that might not transfer electrons, but then we have that very thin layer of polymer, okay, that's a polyion. Then we put the dopant on. And now from a chelated effect, okay, because there are many, many electrostatic interactions, it wouldn't go anywhere. So I think that that's the way we've been thinking about that issue.
Okay. All right.
Okay.
So yeah, my worry was, once there is a diffusion, then you see the optical effects if you're making, for example, LEDs, or if you're making transistors.
You wouldn't see optical effects. And the reason is that the doping level is at the level of a nanometer or less.
Okay.
Okay, we're not at the level of depositing an electron transport layer here. Okay, we are doing very, very low doping.
Okay.
By the way, I was wrong about not including the slide. So here is the slide where Antoine vacuum dopes the graphene, and you can see he takes the work function down to about 2.1. Okay, I'm sorry, about 2.5 with the graphene. Okay, and he knocks the sheet resistance down. Okay, and there's a molecule that I'll show later that's pretty hard to inject in. Okay, he shows that in the absence of the dopant, okay, it's pretty hard to drive current in. If you put a very thin layer of dopant between the graphene and this POPY2, which again, I'll show you on a couple of slides later, okay, what you can see is that they get a 1 to 2 order of magnitude increase, okay, in the current, well, in the forward direction, I'm sorry, it's 2 to 3 orders of magnitude increase, okay, in the current. Now, this goes to the question that you said, Satish, but what if you actually dope the material? Well, if you dope it, okay, you actually go and you make the whole system more or less conductive, and you can see it's behaving less like a diode and more like an ohmic material. Okay, so in a couple of slides, I'll show you what the POPY2 is. Here, I just want to point out, and now there've been a series of papers on this, and this is work. I think this may be our second paper on this, but you can take metal dichalcogenides, moly disulfide, moly diselenide, tungsten disulfide, tungsten diselenide. People have also done black phosphorus now, and treat it with either N or in one case, a P dopant. This is a commercial P dopant, but we'll focus on the N dopant. I'll just mention that with the P dopant, it's sufficiently strong that with tungsten diselenide, you can dope it, okay? But with the N dopant, what you can do is you can start dumping electrons into these systems, okay? And dramatically changing, where they turn on and off, okay, as transistors. And then this is work done with Wei Chen at National University of Singapore, where they just doped bilayer. I think it's tungsten I'm sorry, let me just move this here. Give me a second. I'm not seeing. I think it is tungsten diselenide. You guys can probably see what it is. I have something blocking it. No, it's tungsten diselenide. Yeah, it is tungsten diselenide.
Yeah, we see that. Yes, yes.
Yeah. Okay, because they did all four, and I wasn't sure which graph I was showing. Okay, they dope a bilayer. Okay, and they measure the conductance. Okay, of that, not the conductivity, okay? And what you can see is that when they dope this material, okay, it goes from having a conductance of 10 to the -5, okay, to on the order, it goes up by about, say, 4 to 5 orders of magnitude. And in nitrogen, it's basically flat after a long time. After oxygen, it changes a little bit, okay? And in air, again, it changes maybe an order of magnitude or so, but it basically stays, pretty nicely doped and pretty conductive, okay? Even after, 10 hours in air. Okay, so this is a simple way to go and start playing around with the electronic properties of these two materials. Okay, I'm going to wrap this up more or less by telling a story which is, for us, it was sort of a bit of a holy grail. It was a challenge that we had thought about for years. And what we wanted to do is to use air-stable materials to dope very low electron affinity, ETLs, electron transport layers. And we wanted to do that in OLEDs. And I asked some questions here. Can we dope beyond the thermodynamic limit, which is a question that was asked yesterday? Can we modify conductivity appreciably in these low electron, transport layers? Can we make efficient OLEDs? Okay. And so I guess I wouldn't ask these questions if the answer wasn't yes. This is a paper that was a collaborative effort by Antoine Kahn's group and Norbert Koch and our group and Barry Rand at Princeton. Okay, and in this work, the idea was that we were going to try to use our dimers, okay, to dope a very low electron affinity electron transport material. Okay, so a few slides back, I showed graphene injecting into this material called POPY2. here you see the structure of POPY2. This is a material that is used as an electron transport injection layer in OLEDs. Now, the question is, why did we choose this material? And just to be very frank, the answer is because years ago, we were working or trying to work with Novoled to get a program from them to go and do doping of electron transport layers for organic light emitting diodes. And we spent quite some time working with them, and because they couldn't do it. And we were, there was a real question on the part of, on their part and our part, whether they could do it, we could do it, anyone could do it. And I could say that when we submitted proposals to the National Science Foundation, there was questions on the part of reviewers whether it could be done. So they said, if you could dope this molecule, we take that seriously. And because this is a molecule that we think is a realistic molecule in OLEDs. I'll just say that we had worked out an agreement to work with them, and then it went to the Samsung people, and they said, we're not interested in doing this anymore because Samsung purchased Novoled. So eventually we got funding from NSF to do this. And we decided that we would try to go and dope this material since it was very, very hard to dope. I'll point out two things. I show two numbers here. One is a reduction potential versus ferrocene, okay? And the other is a solid state electron affinity measured by IPES. The numbers are the same, but this is a reduction potential and this is an electron affinity, okay? So here is the scoop. If we took this molecule down here and we oxidized it, okay, that couple occurs at about negative 1.1 volts versus ferrocene. So for this to actually transfer an electron directly to here has a 1.1 volt barrier, okay? That's not going to happen. It's just way too high. It's going to be thermodynamically, thermodynamically problematic if you just think about it as a redox reaction, but it's not a redox reaction because we know that once we oxidize this guy, it falls apart. Okay, but kinetically, it's not going to happen. Now, if we cleave this to make the 19 electron compound, that would have a reduction potential of negative 2.67, which gives us a little over 0.4 volts of driving force to actually reduce this, okay? But the problem is we don't have that, and the problem is that the thermodynamic reduction potential of this material is not that of either this or that, because the thermodynamic process involves cleaving this bond to give you that, okay? And then that could transfer an electron. So what we have to do to figure out the thermodynamic potential is to subtract essentially for each half of the molecule, half of that bond strength, okay? And when you do that, and this was measured, this was calculated, and we benchmarked those calculations against the cases of other systems where we could measure an equilibrium between the monomer and the dimer, but that's another story, okay? You calculate that the thermodynamic potential of this molecule to reduce this, okay, is negative 2.04. So this is still uphill, okay, by 0.2 of a volt per POPY2. In other words, if we took this plus 2 of these, we're going uphill by 0.4 of a volt. Okay, so it should not happen. It should be uphill. Okay, so that's shown here. Okay, what's shown here is a potential energy diagram that says, look, this first transfer of an electron from here to there, it's uphill by 0.4 of a volt. And then if we do the cleavage, which I've told you about, and then we do the electron transfer, we're still uphill. Thermodynamically, we're uphill. Nonetheless, we thought about trying this reaction, recognizing that thermally we could not do it. But what we could do is what people do all the time in solar cells and other things, and that is do a photo-induced electron transfer, okay? And so for the time being, ignore this. I'm just going to show you the diagram of what is going on. And all this says is that if we put a photon in here, we get to an excited state of the POPY2, which means that rather than dumping an electron into the LUMO of this material, we're going to be dumping an electron into the excited state of this material. So we need to look at the excited state oxidation potential. And so what happens is we photoexcite, we create pi star in this material. We get an electron transfer from the ruthenium to the excited state. We now generate a radical anion here, okay, and this cation. What I've told you from the electrochemistry is as soon as we do that, this thing falls apart, okay? So we get a cation that compensates that anion, and then we get a 19 electron compound, which I told you before is going to be 0.4 of a volt downhill for it to reduce the POPY2. So it does reduce, okay? And now I'm going to something which is a little bit of hand waving and speculation. And the hand waving and speculation says the following, that in the solid state, okay, I'm going to have two cations sitting exactly next to each other because they were basically bound to each other. Probably they're going to reorient a little bit, okay, just to kind of mitigate the Coulombic effects. Maybe not a lot, but they're going to mitigate. And now I have these two anions. Now note that this reaction can go right back like this, okay, because it's uphill by 0.4 of a volt, okay? So remember this slide for a second, and now look at this slide, okay? So in this slide, what we show is what happens to the spectra, okay, as we photoexcite. Don't worry about this curvature here. This curvature here is basically an artifact of the fact that we're working on the thin film of a electrode. Okay, you see this band growing in. This band is the radical anion of POPY2. How do we know that? Because we generated it, okay, by another route, okay? So that's the radical anion, and it grows in with time. Now, here is the thing that is kind of interesting. I've talked about this as a photo-induced electron transfer. Now, for those people who have worked in solar cells and in other things, if you get a photo-induced electron transfer and you get a charge separated state that lasts a microsecond, that's considered a very long-lived CT state. Okay, oftentimes you get ultra-fast electron transfer, and then on the order of nanoseconds or tens of nanoseconds, you get recombination. And this is one of the things that we fight when we are making solar cells. Okay, and as I said, our system is 0.4 of a volt uphill. Okay, so what do we actually observe? So what we observe is, and this is all done in ultra-high vacuum, okay, you turn on the light and you see an increase in the conductivity from a few times 10 to the minus 10 to a few times 10 to the minus 3, okay? So we see about a 7-order increase in the conductivity. And by the way, 10 to the minus 3 Siemens per centimeter is plenty for driving electrons into an OLED. Then you turn the light off. You see a little dip, okay? And then this thing, they monitor it, okay, for 100 hours, basically almost no change. For 200 hours, they've gone out to 2,000 hours, okay? They've gone out to a year, okay? And it drops a little more after a year. So I went and I calculated, I said, well, a microsecond, okay, is considered ultra long charge transfer. Okay, this is on the order of 10 to the 13 microseconds. So for those people who are looking for long-lived electron transfer, this is long-lived electron transfer. In other words, we have a system where once we drive it into this thermodynamically unstable state, it sits there by and large indefinitely. Now, why is this? And the answer is, as we know, I will just point out that every single person sitting here is by and large unstable. And I'm not talking about your mental stress due to COVID. I'm talking about the fact that relative to you being you versus carbon dioxide and water, you're thermodynamically unstable. Okay? Yet you exist. And the answer is because there's a non-trivial kinetic barrier for you to become carbon dioxide and water. And so now if we think about getting this molecule back up this 0.4 volts, the first thing that has to happen is we have to transfer an electron back here. Okay? In a bimolecular process, but that's fine because these two things are sitting, but that's uphill by 0.43 volts. Then one of these molecules has to go, and now being reduced to the 19 electron, has to find another one of those. It has to reorient in order to make the bond, which is not going to be easy in the solid state. Then in a second step that's uphill, you have to form the bond because this step wants to go the other way. And then after you've gone through this electron transfer, this reorientation, okay, this bond formation, if you get another electron transfer, then you go back and you get back here, you get back all that energy. But you have to go through all of these uphill steps to get here. And the bottom line is that thermodynamically, that doesn't, or kinetically, that doesn't happen. I actually think there are some pretty interesting OLED manifestations of the fact that we can store charge this way, but that's another thing for another time. So then Barry Rand went and made an OLED. Someone can ask me why he made this stack. And the answer is because he's made a lot of optimized OLEDs, and this was a very good stack for him, okay? And so this has a whole bunch of different things, but the bottom line I want to point out is that they have some, very thin layer of undoped POPY2 to keep it away from this P.PSS and ITO. And I won't go into why they did that. Okay, then they have doped POPY2 and other material, and then they have an emissive layer, okay, and so on and so forth. Okay, so this shows an energy level diagram, but here are the bottom lines, okay? That if you take this material and you try to drive charge through it and it's non-activated, and I'll just kind of focus you on the left side for the time being, okay? It's very, very, very sluggish. If you look at let's take a look here at the current density plot. It's very, very hard to drive current through this system, okay, in the absence of shining light on it, okay? That's shown here. In blue, in the solid line, if you irradiate it and you dope, you can see that at 3 volts, 3.5 volts, the thing turns on. This is a log plot, right? And you can drive current through. Okay. Now, here are the things that's kind of weird and interesting. And you'll see that there's a luminance plot below that parallels the current plot. The thing that's interesting here is that they do this 10 times. Okay, they turn it off, they turn it on, they turn it off, they turn it on. Not surprisingly, the dope system where you shine light on it doesn't change. Surprisingly, the system where they never turn the UV light on to dope the material, okay, after 10 times looks like the system where you turn the light on. And by the way, these make good OLEDs. I mean, they're 18% efficiency OLEDs. So the question is, why are these materials working when we don't turn the light on? Well, what we speculated is that the first time it takes a high bias to get the thing to turn on, but it turns on, okay? And once it turns on, it generates some light. And we can see that it's generating some light here, okay, mind you, at 7 volts, but it's generating light. So, well, we said, well, maybe the light itself is activating the doping. And that once you start cycling it, you generate light that activates the dopant, and then eventually the system's doped. Well, that's all well and good, except for one thing. Every one of the materials that we put into this system only absorbs in the ultraviolet, and we're making a green dopant. Okay? And so then I recalled work from my old organometallic background of people making charge transfer complexes with metallocenes. And so I said, you know what? I bet that you're making a charge transfer complex with this metallocene, and that has an absorption in the visible. So they looked and they measured the absorption spectrum, and they could see nothing. Okay, they just couldn't see anything. I said, well, that's the only way I can imagine that this thing is working. So my speculation is you formed a CT complex in the visible, okay, that is absorbing light. And now you get that, okay, you excite into that, and then you get the charge transfer. From that point on, it's the same. So I'm not going to go through this, but what I will tell you is that that is exactly what is happening. And that what they did was they made a solar cell out of this. And then they did what are called ultra-sensitive EQE measurements of the solar cell. And they can show that if you excite the solar cell down to 600 nanometers, 650 nanometers, you can generate tiny bits of current, okay? Nothing like if you're excited into here, but enough that you were basically exciting these CT complexes, okay? This is work that kind of was pioneered by Koen Claes, okay, Koen van der Waal, when he was working with Alberto and then done later. So what we've now shown is that you don't even need to photo excite these things, okay? You just turn it on, okay? And the CT complex will get this thing going. And what that also means is that if you ever made a working device, first of all, if it was out in air, in the light, you'd be exciting that CT complex with whatever light you had around, okay? And that could be enough to get this going, I guess, if you did it long enough. But you could still just drive it, okay, a few times, and it would turn back on. Okay, the last thing I want to point out is that that these things can be not only metallocenes, but we can make these things using DMBI and dimers. We worked on this with Zhenan Bao. We've now made, for example, the standard DMBI dimer on like on the order of 15 grams of it. Okay, we've optimized the synthesis. We can make if honest to God, if someone told us that we needed a kilogram of this material in our group, okay, we could go make this material by the kilo. As I said, we've made 15 grams of it. So we have for what the world needs, who use it on, milligrams at a time, essentially an infinite supply. A couple of other things. We've used these dopants with Diane Pei, both the hydride dopants and DMBI2 to dope some high performance N-channel polymers. This paper came out last year where we're seeing conductivities on the order of 10 Siemens per centimeter. This paper just came out online in November. It's out. This is a polymer now where we can dope these materials with the dimer or the ruthenium. In this particular case, I'm sorry, not the dimer or the ruthenium, the hydride or the ruthenium dimer. This particular case, for reasons that I can discuss, works a little bit better with the hydride than the ruthenium dimer. Well, the bottom line is the ruthenium dimer is too effective and it dopes this thing too quickly in solution, and it doesn't set up the right morphology as it's forming the film. Whereas the hydride is less effective. It doesn't dope until it's in a film and heated a bit. Okay. And as a consequence, we can get this material to form the correct morphology in the film prior to doping. Okay. As a notice, okay, here's a kind of a zoo of dopants that have been made. I can tell you that, this has been made by Adam, I think, Moulet. A lot of these have been made by us. This is a dopant that's been reported in the literature. We've made this on gram scale and have it. It's an effective dopant. It's not very soluble, okay? All of these dopants here, we have, and they're available to people for collaboration. Okay, so yeah, on this slide I show these are dopants that our groups has made. Okay, I said there were 8 to 9 grams available. That slide is old. There's on the order of 15 grams of this stuff available. So if people need these dimers, okay, or they need dopants that have several hydrides and things like that, let us know. We're happy to collaborate. And that, my friends, is that.
Okay.
So,
thank you.
I'm a little late.
That's
I'm 3 minutes late.
Yeah. JD?
Yes. Thank you, Seth. Thank you very much for these 2 lovely talks. Today's talk was more into applications and lots of very interesting molecules and chemistry. So thank you for showing that.
You're welcome.
I would like, yeah. No, so
Go
I
on.
would, yeah. So we will open the floor for some questions and then conclude. Any questions, students?
Yeah, particularly.
Yes, Ravi. Okay, Professor Ravi Kishore had a question long back, so I will let him ask the question. Yeah.
Yeah, Sid, very nice talk, very interesting work. Yeah, a lot of it actually. Yeah, so one question is, you're talking of filling up the trap states, right? There are 2 options there. One is to remove the trap states and the other is to fill it up. Now, which do you think is a better option from the efficiency point of view and also the device life point of view?
Well, my personal feeling is if you can remove the trap states, go ahead and remove the trap states. But as I said to you, with organic materials that are molecular, it's a very different game than making a ultra high purity inorganic semiconductor. So I think that if you can remove them, and with sublimable materials, you can certainly knock them down, go ahead and do that. But there are enough cases where I think you may not have the capacity to do that. Okay.
Yeah,
the other thing I want to point out, right, is that if you're going to use the dopants, there are 2 approaches that you can use. One is the one that we just described today, which is to use something that's sufficiently strong that it can dope the trap states, but also dope the the LUMO of the system. And there you have to be super careful, right, to not put too much dopant in, okay, that you'll actually start doping the system. The other one is to have dopants with a huge range of ionization energies so that you can just choose one that is more or less only able to thermodynamically dope the trap states, okay, and not really able to get up to the LUMO. And that in itself, I think, may afford you some additional flexibility, but you have to realize that there's going to be a distribution of that you'll end up with an equilibrium. And so you still have to be careful about not putting too much dopant in. But I think that there are different approaches. But if I had the ability to take a material and sublime it 5 times, okay, as is probably the case in the OLEDs that are in your telephone, and get it pure enough that I don't have to worry about this, I would certainly do that. But if I'm going to go and deal with polymers or a solution process, if you deal with, let me just tell you this, if you deal with solution process materials, okay, you have to make sure that your solvents that you're using to deposit the materials are absolutely pure, absolutely water-free, absolutely oxygen-free, okay? If you can do that all the time, all the more power to you. But I think that that's a challenge, practically.
The other question regarding, you mentioned about this interaction with boron compounds.
Yeah.
That would be H2O, and depending on the molarity, depending on the mole ratio, you have different crystal structures, right?
Well, I didn't have different crystal structures.
I mean,
My PhD advisor, my postdoc advisor 22 years ago published different crystal structures. Yes.
Right. So in that, the charge was, if you look at the anions, the charge was highly, like it was a big molecule and the charge was delocalized.
Well, I don't know that for sure. And I don't know from a mixed valence kind of Robin Day point of view, whether these are so-called class 1, class 2, or class 3 mixed valence compounds. But it could certainly could be delocalized.
But then
Yes.
are you able to form an ion pair there with that sort of a huge delocalization?
Yeah. So what he's asking, I guess, is a diffuse ion, large ion, can it form an ion pair? Yeah, with the P3HT and other kinds of.
So that's a very interesting question, which is one of the questions that we actually framed in our DOE white paper. Okay. And then the question is, could you have a Lewis acid that is going to form that? And if you think about it, right, if the anion was going to be super delocalized, then would it actually be a really good Lewis acid in the first place? Or would you have toned down its Lewis acidity to the point that it wouldn't be a great Lewis acid and go through this process? And so that raises the question of, are there ways to strategically think about systems that form highly delocalized things in a secondary step? Okay, and these are all very good questions that I think need to be explored. But I do think that having the reaction that forms the thing provides the driving force, right? Because essentially, if it was highly delocalized in the first place, you wouldn't necessarily shift the thermodynamics. You'd kind of have that already built in at the outset, and you wouldn't get that thermodynamic gain necessarily. So that's my initial thought, but I could be wrong. Okay.
There are 2 questions from students. I would like to take them. Abhishek, could you unmute and ask your question?
Yes. Abhishek.
Hello.
Yeah, go ahead. We can hear you. Yeah.
Nice talk, Seth. So I have a question regarding the solution phase doping of polymers. So when you have, if you are lucky enough to have a common solvent in which both your polymer as well as your dopant is soluble, otherwise, how does the solvent polarity as well as the solubility dictate the doping procedure? Like if you have a partially miscible solvent, then how does the chemistry, does it change altogether, or the dopant becomes ineffective, or how does it play? Like if you can give some anecdotes regarding this. And the second question is regarding the vacuum deposition of some of the hydride based system. For example, the slide shown over here, they are like quite big to me. If you can really vacuum deposit those molecules without breaking the bonds, I just curious.
So that's a very good question. So I'll just tell you that initially on some of the molecules, I don't know. Initially, in the case of some of the dimers, the whole point was literally that when you vacuum deposit, you break the bond to make the highly reactive species. It turns out that only in a very few of these systems, okay, does that actually happen. In these rhodium systems, it happens. In these ruthenium systems, when you vacuum deposit, it goes in the air as the dimer. That we know, okay? And we know because we've done deuterium labeling studies where we vacuum deposit a system where you have deuteriums and a system where you have hydrogens, and we look for what we call crossover, where if they fell apart and they came back together, if you took DD and HH, you'd end up seeing HD. And how we did that, it's a little bit complicated because we had to do it using some careful NMR studies. In the case of the DMBI dimers, it turns out that if we put a ferrocene here, okay, and maybe a cyclohexyl group, we can actually, I think it's might be the cyclohexyl. We can actually do experiments using EPR where we can heat and we can detect the radicals, okay? And we can do temperature dependent EPR and see that these things fall apart. In many of these hydride cases, we've not yet attempted to vacuum deposit, but for example, this compound, no, this compound was solution processed, okay? So I don't know whether every one of these things can be vacuum deposited, but I think a lot of them can be. I'll make a comment here. This material that I mentioned can be vacuum deposited, okay? It was first reported by a group in Germany. So just to be clear, the compound has been made like 40 years ago by folks at DuPont. Okay, so this compound is really old as the hills. Okay, this compound has, you know, it's not a new compound, no more than this compound that I show here, which I point out that our group introduced as a P dopant. Okay, but was made in 1962. Okay, so these things existed in cases, but they hadn't been used. This guy was used as a suspension, okay? And that is problematic in some cases, but what you're seeing now is that more and more people are doing this process called sequential doping, where they deposit a layer of dopant on a preformed film and then thermally drive the dopant into the film, okay? And I would just say, and I would just defer to having a discussion like this offline, that there are advantages and disadvantages. The advantages is that you have to count on the fact that if the material is not soluble, that you have to count on the diffusibility of the dopant into the film, which if you want to dope a thick film could be very problematic. But for example, if you want to have a film that you only dope at the interface and that you don't dope throughout, could be advantageous, okay? And then the issue of the solvent, it depends. I mean, the solvent is not going to, in the final analysis, necessarily determine where everything ends up thermodynamically, but it will have a large impact on the kinetics, okay? And so I talked to you about a case where where our dopant was too fast, okay? And it led to formation of charged species in solution, which aggregated, and we didn't get an ideal morphology to get the highest conductivity. Okay, so you could begin to think about using your solvent one way or the other to accelerate the doping process in solution if you want to, before you form the film, if your dopant is maybe too slow, or you could try to back off on the solvent polarity, assuming you could keep things in solution, such that until you get the thing into a film and the concentration goes really high, you don't get doping. So I would not say that this is a kind of a better or worse than. I think that what you need to be thinking about is exactly what would all these issues that you raised, the solubility, the solvent polarity, due to the doping process, and under the very specific conditions that are required for your combination of dopant and material and film, what is the best way to use those things to get where you want to be?
Okay.
That's my view.
Thank
Was
you.
another question in the chat.
Yes, there is one more question by Konad, another student of Satish's from IISc Bangalore. Konad, could you ask the question?
Yeah, just a small question, sir. You were talking about this triaryl boron molecules and isolating them for characterization. So I was just wondering, how do you isolate them, and what are the how stable those intermediates are? Not intermediates, like how stable those hydrogen bonded boron boron molecules are, which you're studying for characterization.
I didn't do that work. I'm telling you, that was work done by my postdoc advisor 22 years ago.
Okay.
And sadly, he passed away last October. So I can't ask him. Okay. But I would tell you, I would bet that they're not ridiculously sensitive. I bet that they're not that hard to isolate. Okay. And in fact, I mean, what I recommend you do is go and dig out this paper here.
Oh, okay, sir.
Okay. Because in this paper, okay, I would bet, and I might even have it available, right? But in this paper, okay, I know Malcolm. He was a synthetic chemist. Okay, so if he made it, he will tell you how he made it. Okay, and that will answer your question.
Okay, sir. Okay, thank you so much.
Now, what I'll tell you though is the thing that you need to consider is that what you're going to have a hard time getting your hands on is not this. Okay, what you have a hard time getting your hand on is the metallocene that they happen to dope. Okay, because the neutral compounds, well, no, because they did it with ferrocene. So so I bet you can just take ferrocene, okay, and the boron, and repeat what they did. Okay. I bet it's pretty straightforward. In fact, that's my guess.
Okay, sir.
Yeah.
Okay.
Vivek, Professor Vivek Tiwari had a question.
Yeah.
Yeah, thanks, Professor Marder, for a very interesting talk connecting concepts of organic chemistry and physical chemistry together.
Vivek, audio is really super bad.
Yeah.
Oh, is it still bad or?
No, it's better.
It's
not perfect. It's not perfect, but it's better.
Okay. If it's not good, then maybe Jyotishman, you can convert.
Okay, I'll just read out the question regarding dopant-induced energy transfer. Vivek is asking regarding dopant-induced energy transfer. Is it possible that once excitons are excited within the donor, the dopant layer simply converts them into non-emissive polarons, and that also contributes to PL quenching of the donor? So what do you mean?
I mean, I guess that if that were true, then the experiment where they shifted the energy levels around a little bit should not have led to a large increase in the photoluminescence efficiency. And so, I would say that the evidence that we have is not consistent with that, unless I'm missing something.
Okay. And
now, hang on. This leads to another interesting question, though. Okay. And that is, how much does the dopant affect on the photoluminescence of the material?
Yeah.
So I see what you're saying. And so that could be a concern. So a concern that you can have but didn't seem to be the case in the OLED that we made, is that the dopant leads, the polaron of the dopant leads to quenching of the luminescence. So in the case of the energy transfer, the thing that you need to realize is that we basically have a monolayer of dopant, okay? And so, so that's one thing. The other thing is that while I didn't get into it, I'm absolutely certain that when Barry Rand put this device structure together that I showed here, which has 18 jillion layers, okay, that by and large, okay, he put in things like this 10 nanometers of the TBI between the iridium dope layer and the dope layer, probably to manage exciton diffusion and things like that, okay? So that you didn't have the doped layer in direct contact with the emissive layer, okay? And, I'll also say that if you have, as I do, I have an OLED TV, okay, and I have an Apple. I had an Apple iPhone 10. I now have the Apple iPhone 12 Pro. But if you have a Samsung phone, okay, it has doped HTL materials in it. Okay, so clearly what they've done is they've figured out how to keep those potential exciton traps, okay, sufficiently far away from the emissive layer that they can mass produce essentially probably today, damn near every cell phone that's made in the world, okay? So I think that it's clearly a physical problem, but it's also clearly one where the engineers have figured out how to work around it.
Thank you.
Okay. Okay. Thank you.
Let me make one last comment. I would say that people have talked about using doping in OPV systems to modulate conductivity and things like that.
Yeah.
I would be mindful that if you tried to dope the active layer of an OPV, that polaron quenching of excitons could well be a problem, and I think that that's something that people have been very mindful of.
Yeah,
it does affect. It does affect.
Does affect.
Yep.
Seth, I think there are papers which are seems to be controversial in that regard. Yes, it does affect.
Okay. Yep, I agree.
Okay. Well, this is fantastic. I really would like to not, prolong this session. And Seth, big thank you from both Satish and me. And we are so delighted and so fortunate to get this so much of enthusiasm from you, as well as, of course, the enriching experience of learning from you. So we are delighted that you did these 2 sets of tutorial talks online. I know the medium is difficult to work with sometimes, but hey, you can do it from your home. So we really thank you.
My home and
with the coffee mug. Yeah. So I would also like to thank everybody in the audience for active participation in however much you could, and also especially the students who asked really important questions yesterday as well as today. I just wanted to make an announcement that the YouTube video of yesterday had an issue with live streaming. It's going to be put up very soon in the YouTube channel. We were going to send this information right back at you, how to figure it out again. Everything has been recorded, so do not be worried. We will be able to hear Seth again and again on repeat mode. Okay. So with that, I would like to call for ending the session. I just request Satish if he has one or two parting words.
Yes, I think I would be repeating same thing. What it is indeed a pleasure to hear you, Seth. Thank you very much. I think, as you mentioned in the beginning of your first talk, where you said that understanding science requires a lot of efforts. I think that certainly motivate our students. These two talks were so in depth and very, very deep analysis. I think that will motivate many of all of us, including our research groups. So thank you very much for giving these talks.
Well, I'd like to thank you both for actually approaching me, but also, you could give a seminar and be talking into your TV screen or your camera and TV screen, is the case here. But it is so much different when people are popping in and asking questions. And I really do appreciate the level at which this was a discussion rather than a monologue. That's very special. And I will remember that fondly for a long time. Thank you guys so much.
Thank you. Thank you. And Satish and I will be sending soon something as a token, okay? For this.
Okay.
Thank you.
Thank you.
Take care.
Yeah.
Ciao.
Ciao.
Bye-bye.
Satish.
Okay, good. Thank you. Take care then. Bye-bye. Cheers.